All right, let's do pendula. We're doing oscillations. Oscillations are very useful for physical, large-scale things as well as atomic, molecular scale things. So oscillations are critical. We've talked about springs. And so we've got the case of a horizontal spring. We can do a vertical spring. Now we're going to talk about pendula. So something that swings back and forth this way, knocks into something there, got a collision, energy loss, oh my gosh. Right? Here's a pendula, things are swinging. And we're going to see, how do we deal with this? Here's something else that's swinging back and forth, and that's kind of a big old mess. So what's the difference here? I could take this guy and I could swing it back and forth, and that's kind of weird, right? So I don't know about that, but you can do these things. I can take just a simple rod and I can hold on to it and have it swing back and forth. I can put a pin through it and hopefully the friction is not too much, but if it is, it'll just die out. So we'll talk about that. So how do we do this? So we're doing simple harmonic motion, SHM, which is a very special case of oscillation. It's a sinusoidal oscillation. As I've mentioned, a sinusoidal oscillation can be used to build up mathematically, any other type of oscillation, Fourier analysis. Okay? So it's really worthy of your time to master this. Now we looked at it by kinematics analysis, looking at it as the shadow or the projection of rotation. We looked at it by energy analysis, which is pretty easy, particularly when there's no losses of energy, conservation of mechanical energy. And we looked at it with Newton's second law. So Newton's second law gives us the classical simple harmonic motion differential equation. We've got cases of a horizontal ideal linear spring, and we've got vertical. There aren't a lot of different problems like we did before, all the beams and ladders. There aren't that many problems. We're going to now look at the case of pendula. Now, a lot of people will do the simple pendula first because it's kind of simpler, but in fact the compound pendula is just as simple. So the compound, or physical as it's sometimes called, pendulum, and then in the special case we have the simple pendulum. The simple pendulum means that the object going back and forth is small compared to the length of the string or whatever it's on. And the length of the string is such that it's a negligible mass, not a factor. Okay? So that reduces very nicely. In this case, I'd probably say, a simple pendulum, that's a pretty good model. Didn't want to do that yet. Here, the object size now is much more substantial compared to the length of the string. Now, it's getting closer to a simple pendulum. How close do you need? Well, it depends on what you're doing. That's getting closer. The object can be treated as a point mass more and more and more. I don't have to worry about the shape or the size. That's getting better, right? Simple pendulum. Here's that's really complex pendulum. Sometimes you'll get rotations within rotations, so things have different modes of oscillation. That's usually upper division. Here's something, I don't know, physical, complex. It just depends on what I need, right? Let's do this thing. All right, so how do we do it? We know we want for pendula to do the Newton's second law for rotations. So let's just write that. So pause and write Newton's second law for rotation real fast. Start from the beginning. All right, good. So you've got Newton's second law for rotation, which is the sum of the torques on your object. Causes angular acceleration times I. Now, as you saw with the spring, we're going to write this a little differently. This is the rate of change of the rate of change of angular position. Okay. So remember, F net causes acceleration linear, A, which is the second derivative of the position function with respect to time. So it's a very similar format. It's going to have a very similar form, a couple little twists. All right, so that's it. So that means, okay, well, that means I do the good old torque analysis again, I guess, but now I can't add them to 0. So I look at my object, and here's my object, some blob. You can call this blob Bob, since it kind of looks like a person. So here's Bob, and I need Bob's center of mass, because the only forces are going to be at the hinge, and then the force of gravity. So, fine. Where's Bob's center of mass? I don't know. It's pretty long over there, so maybe right about where his heart is, ish. Okay, and so I'm going to draw that force of gravity, nice and clear so I can see it. I'll use a capital M, doesn't matter, but I'm just going to use a capital M, G. What are the other forces? There are other forces. There's the hinge, right? There's the whatever. This is probably HY, and then maybe there's an HX over here. All right, cool. That's how you do it. You choose your object, you draw in your forces, then you choose your axis of rotation, and X and Y directions. But I'm going to use rotation. So I'm going to choose my axis of rotation right here. And so that tells me that the torque around A from HX is equal to what? And the torque around A of HY is equal to 0. So clearly I don't need to worry about, I've only got one torque. How easy is this? We've done beams and ladders, for goodness sakes. We can do this. So here we go. I need to define some variables. And so I'll define these variables. Calculating torque. I've got R is from here to here. Now, different books use different letters. Some books use capital D. That's kind of nice. The Knight book, which I like, uses the lowercase l. That's fine. It's not the full length. It's just wherever the center of mass is located. Okay, cool, fine. So there we go. Now what do I need to do? Well, I need the torque from that guy. So I've got the torque from mg is the only force exerting a torque around that point. And that's going to equal I of Bob. But not I of Bob in general, I of Bob around A times alpha around A, the angular acceleration. Some interesting things come up here, so don't go to sleep, but do just take one step at a time. One mini step. Guide yourself through. That's how we do the real work that you get paid for. All right, so I need the torque. Oh yeah, I've got those 3 ways, really 4 if you include the vector cross product, to find torque. Which way do I like? Doesn't really matter, right? You've got, let's go over here, torque equals plus or minus RF sine alpha plus or minus R perpendicular F plus or minus RF tangential, which we call that perpendicular to the line of R. I like that one in this case for visual. Now, if you see, here's R, here's the line of F. It's not so bad to go the shortest distance from A to the line of F would be right there. So that would be R perpendicular here. Here, make sure you see that if you don't ask someone some questions. I kind of like seeing what part of that force right now is torquing or pulling Bob around so that Bob oscillates back and forth. So let's take a look at that. Well, I need the part of mg perpendicular to R. The line of R is here. So that's going to be perpendicular. I can draw a line perpendicular. It's a component, so I like to use dashes. I don't keep going down to here, right? If I went down to here, that doesn't make sense. Because these are components and they're not perpendicular. That doesn't. I need to head down here and here. Of course, you can draw that up here. But hey, is that torquing? Heck no. That's not going around A. This is going around A. So this is F perpendicular. All right, what can I say? Baby step. What's F perpendicular? F perpendicular to the line of R. Well, let me put it in terms of angles. What angle might I know? I mean, as it goes back and forth, what angle is changing? It's this, right? There's my angle. Angle away from the center. So that's going to be theta, and it's changing. So theta is a function of time. So you're learning something a little bit new, how to encode this. All right. So that's a pretty big angle. That's a small angle. That's a big angle. That's got to be theta t, right? That's a small angle, because I drew it exaggerated. So where's theta t? Oh, it's got to be the big angle. Theta t. Just basic geometry. That's not physics. It's a tool that we use in physics, but make sure your geometry is cool. So F perpendicular is positive or negative. This is a little tricky because it'll be this way, counterclockwise around A on this side. If it swings over here, it's going to be clockwise. And this is tricky, and I'll tell you the answer so you don't have to figure it out. It is in the direction so as to reduce the angle. And so we would say it's negative because of that. It's in the direction so as to reduce the angle. Okay. Well, actually, sorry. That's going to be for the torque. The torque from mg is negative r f perpendicular. That's what I want. So is F perpendicular is, wait a minute, that's mg, that's the force. And it is opposite, so that's sine of theta as a function of time, because that's going to vary. It's the only difference here. Now I can go here. Sorry. That now is, this is going to go where? This is going to go up there. That is this. All right, I'm messing around, just whatever. I'm not sure where I'm going. I am. But yes, it's easier for me because I've done it. The first time's always harder. So here we go. Let's do it. I got the torque from mg is negative r f perpendicular. Negative because it's reducing the angle. D squared dt squared of theta. That is alpha right there. All right, fine. What is it in particular? Negative. Oh, r is from the axis to the point of application. That's L. F perpendicular is mg sine of this varying angle. All right, that's cool. I'm going to erase. This is just, that's a mess. What did I say? I of what? Of Bob around that thing. Okay, fine. D squared theta dt. I'm not even thinking now. Fine. Fine. So I can do this. I can say, I can rearrange. Remember how we rearranged with the linear spring. So I can now rearrange. I need to solve for it. So my objective here is solve for theta as a function of time of the compound or physical pendulum. What is that? Angle. Okay. Now that problem is going to be tricky to do. You're going to need some techniques with differential equations and stuff. But the good news is we can play with it. So let me get it into one form, and then we'll cheat, which will work fine. So recall, for the case of a spring going back and forth, the Newton's second law, make sure you can do this just cold in your sleep, the Newton's second law became the second derivative of the position with respect to time, the acceleration, was equal to negative a constant times the function. Rearrange that real quick, you should see F equals ma for a spring. So if I get that form, that was the classic simple harmonic motion differential equation, right? So let me see if I can get that into that form. Let's get I d squared theta t dt squared, put that on that side, put that on the other side, is equal to negative L mg sine theta t. I'm not going to worry about all those things that are worrying me right now. I'm just going to move forward. That's m times g. Free fall acceleration, but this is certainly not in free fall. All right, that's looking a little closer. A little closer here. So make that model. This is our goal, right? We're trying to get it into the simple harmonic motion form, which is the second derivative of position with respect to time is negative a constant, that was the spring, times the position function. We know what that answer is because the sinusoidal sine or cosine function, when you take the derivative twice, gives itself back with a negative and a constant squared. Cool, so I'm close. Oh, let me just get, can I just do this? That's looking pretty good. I got my negative. That's good. I got my constant. Oh, shoot. Oh, no. I don't have the function of position as a function of time. I've got the sine of that. So it's looking pretty close. Remember where it came from. Just simple. I got one force. I got one torque. I just stick it in there. Put it in the form. That's new. What am I going to... Well, if that was d squared theta of t dt squared equals negative L mg over I times theta of t, well, then I'm good, because that's exactly the same form. If that's true, then I could say, hey, I know the answer to that, because if theta of t were equal to some amplitude, but in this case, that's theta max, that's the maximum angle that I pull it back, times the sine of omega t, or the cosine. It doesn't matter. Either one, when I take the derivative twice, I get it out. And you can shift your starting point with that phase angle, which is a constant. Well, I know that'll work. I'll take the derivative twice. I'll get negative cosine, and I'll get omega squared out here twice. And that'll be omega squared. Ha! So then I've got omega would equal the square root of L mg over I. If I could do that, that'd be fun. But can I do that? Can I justify that? Yes. In the special case of small angles. And so you really need to do this is write up a table here of angles in radians. Try it in degrees and see how it fails. Okay. So put your calculator to radians, put in 0, get the sine of that. You're going to get, that's easy, that's 0. What about something small? 0.0001 radians. See what you get. 0.001, 0.01, 0.1, 1, 10. It's going to get a bigger and bigger difference as you go down. So at some point, at what point? Whatever point is good enough for your application. So whatever. But these are approximately equal for small angles. That's a small angle approximation. And so yeah, in fact, I can turn that into that, but with the caveat that this is for small angles, and I know that as the angles get bigger, well, the deviation between reality and my theoretical model will get greater. So here's my answer. Now, tricky, little bit, fun. That's why it's on video, though. You can hear it, you know, fourth or fifth time, that's when you really clicks. What's omega? Well, remember, that's the same as 2 pi times the frequency, which is 2 pi over the period. And you can count how many cycles per second. And then figure out the seconds per cycle. Multiply times 2 pi. L is constant, M is constant, G is constant, I is constant, and so that's a constant. And so here, we realize the value of videos because your brain's exploding on the first time. And that is that omega equals the square root of LMG over I, just to reinforce this, which is 2 pi f, which is 2 pi over t, repetition's how you learn it, is a constant of the motion. You said, yeah, you just said that. Yeah, but wait. This is called angular frequency. Fine, but you know what? We got an oscillation and a rotation now. It's going back and forth, but it's rotating. And so what is the angular velocity? That would be a bad letter, so maybe I want to use something else. In fact, it's just too confusing. Well, I know what it is, though. The angular velocity is d theta dt. Which is sinusoidally varying. As you know, it's going to speed up and slow down. That's the angular velocity. And that is not a constant. That's the angular frequency, which is a constant of motion. That's a lot to keep straight, but it's actually not bad. And if you do it, if you push yourself and do it, man, that's really solid. Now I got one more little bit on this. All right, multiple. A. Erase it and do it. B. I promised you a bonus. And the bonus is that omega of a compound or physical pendulum, where I'm talking about the angular frequency, which is a constant of the motion, which is equal to the square root of L M G over I, whatever I is for Bob, if you hang him by his head right there like that, gives you the simple pendulum where you have this and that's M. And as you pull M to the side, oops, I've got that L as the length. And what's I for this? I for a simple pendulum is ML squared. And so I've got omega for a simple pendulum is root LMG over ML squared, which is root G over L. Which means the mass doesn't matter. But you know that because you've dropped things. And gravity is the player here. And so that makes sense. You've got a mass hidden in here. You just don't know exactly what the formula is because it's a weird shape. But the mass goes away. G, it depends on what planet you're on, right? So more force, faster oscillation. We said that with springs. More inertia, effectively, slower oscillation. We said that with springs. And finally, let's check it. So let's check it. And we've got our... All right, here we are. Let's do this. All you got to do is take something, stick it on a string, and you can count. You know, do it for 10 seconds, how many cycles, or do it for 10 cycles, that's easier. And then time it. 2, 3, 4, 5. Oscillation is going to be slower or faster? 1. Whoa, that's quite a bit slower. Right? All right. So you can see it. You just go like this. That's slow oscillation. That's fast oscillation. Does the mass matter? No. You could test